Now we will move to the steady-state, two-dimensional, two-energy groups, multi-assemblies reactor modeling. This type of problem is close to the real-world reactors that consist of multiple assemblies. We will solve the rectangular cores first, then move to the modeling of reactors with hexagonal assemblies. First, I'm going to recap the important relationship between the cross-section and also the MATLAB coefficient. So the first part is the PDE coefficient, and the second part is the boundary condition. So you need to follow those equations or relations in order to set up your model in MATLAB. Again, we will use one example to demonstrate how to perform this kind of modeling. So here we have Xeon-1 power reactor model. This is a simplified model derived from the Xeon reactor. So the Xeon nuclear power station was built in 1973 near Chicago. It has two Westinghouse pressurized water reactors, and each unit can produce 1 gigawatt of electricity. These two reactors were decommissioned in 1998. Okay. The core configuration is shown on this figure. You can see that this core is made of multiple square assemblies. This figure only shows 1/4 of the core. The actual core will be 4 times larger than this figure. The number inside each assembly represent the material index. So you have material 2, material 3, material 4, and material 5. This model is simplified or is modified from the reference 3 by removing the material 1 to give you a simple model. So in this table, you see that you have 5 materials, but the first material will not be used. We only use the material 2, 3, 4, and 5. Again, you will have the diffusion coefficient D, absorption macroscopic cross-section sigma A, your fission cross-section mu sigma F, and also your scattering cross-section from group 1 to group 2. Now we will move to the MATLAB to demonstrate how to solve this problem. This photo is the satellite image of the Xeon power plant before the decommission. And the reactor is located inside this cylinder concrete building. One cylinder building houses one reactor. They have 2 reactors. Currently, there's nothing left there because the power plant has been decommissioned and the building has been demolished and removed. Okay, before we do the MATLAB demonstration, you need to log on your Blackboard. Okay, log on Blackboard and click the computer application. Then go to the course content. Then scroll down until you see this script for power calculation. You need to download this zip file and place it to your MATLAB working folder. Okay, place it to MATLAB working folder. And then extract it there so that those files will be in the same folder as your developed script. Okay, now I'm going to just put it away. So here it is my MATLAB working folder. You see that we should have these three files plus this one. In this rectangular model, we only need to use this file. Okay, make sure that this file is located at your working folder. Then I'm going to show how to solve this problem. Okay, PDE tool. I'm going to turn on the grid. Okay, change this one to generic system. And I'm going to draw one assembly first. Okay, draw one assembly first. This is our first assembly. Okay. In addition, this figure shows that shows the 1/4 of the core, but we are going to take the advantage of this symmetry and only model the 1/8 of the core. Okay, just 1/8 of the core. We are going to place the origin at the center of this core, and we draw the very first assembly. So for this one, we are going to place this one as the center assembly, so that the lower left corner coordinate will be 0 and 0, and the y is the assembly pitch or the side length. Assembly pitch is the center to center assembly distance. Okay, press OK. Next, we are going to adjust this access limit. Okay, so the assembly side length is 21.608. Then along the x direction, there are 9 assemblies. Okay, so the 21.6 times 9, it is slightly lower than 200. Okay, so we set it to 200. This one set it to -10. For the y, the same. 200. Apply. We can also turn on the axis equal, so this one will be a square. Next, we are going to duplicate this assembly to form the first row. So we select R1, press Ctrl C, then press Ctrl V. Here, for the first row, there will be no y displacement because everything will be on the same y coordinate. And each of the assembly will be moved 1 pitch to the right, 21.608. The first row has 9 assembly. So we already have 1 assembly here, so we need to generate 8 more. Okay, generate 8 more. So the first row is completed. Next, we are going to generate the first assembly in each row, in each of the other rows. We select R1. Okay, select R1 only. Ctrl C. Okay, press Ctrl C. Then Ctrl V. This time, we are going to generate the diagonal line. So for each newly generated assembly, it will move to the right for 1 pitch. Move up 1 pitch as well. So we have 7 rows. We already have the first row, so that we need to enter 6. Okay, so everything is here. So we are going to repeat this process to complete all those cores, all those assemblies. Okay, we select XQ9, Ctrl C, Ctrl V, 21.608. So this time, for the second row from the bottom, I'm going to generate 7 more. Okay, 7 more. Ctrl C, Ctrl V. 7 more, then 5 more. 6 more. Okay, 6 more. 5 more. Four more. So this is 2 more. And 1 more. Okay. Now we need to save. Okay, I'm going to save as this one. Neutron diffusion example 3 model. Press save. Okay. Next, I'm going to draw a triangle to perform the cut. Because we are going to model 1/8 of the core, therefore we need to cut this unwanted region. Okay, we use this polygon tool. Okay, polygon tool. So click, then hold, then release, and do again. So this is a triangle, and we want to use this triangle to cover all those unwanted regions so that we can perform a cutting. Okay, we double click this one, and we need to precisely adjust the coordinate of those vertices. So we start from the very first one. Okay, this will follow how you draw this triangle. And I draw from the origin, then here, then here. So the first one will be the coordinate of my first point. So it should be located at the origin. So enter 0. Make sure you press the tab. So after you enter this coordinate, you need to press the tab. After you press the tab, you see that here this 1.5 will be changed to 0. Okay, change to 0 so that your value has been saved. Press 0 and enter 0 and also press the tab. Okay, when you press tab, you see that the coordinate will be changed to 0 and 0. Go to the next one. Okay, so next one here, it can be any value as long as it is on the y is equal to x line, and also it is large enough to cover all those triangles. Okay, so we can use 170. Make sure you press tab. If you do not press tab, you see that if you use your mouse to change it here, this one is not changed. Means that its value is not saved. So 170 and 170. Okay, make sure that this coordinate is changed to what you want. Then go to the next one. Here will be this point. So apparently it is 0 and y is 170. Okay, 170. Before you click OK, double check all those values. Make sure that those values meet your expectation before you click OK. Okay. Now it is precisely cover those unwanted region. Okay. And save it. Next, I'm going to recommend you go to the mesh mode. Okay, go to mesh mode. Oh, I need to. I forgot to change this set formula. Okay, so we need to use the union of all the squares. Okay, the union of all the squares. Okay, except the P1, everything is the squares. The union of all the squares, then minus the P1. Okay. So I use the bracket to enclose all the squares, then minus P1, because the minus has higher calculation priority in MATLAB PDE Toolbox, so I need to enclose everything inside this bracket. Next, I would recommend you go to the mesh mode first. Okay, go to the mesh mode first. And we are going to generate the mesh to see if the mesh quality is good. Use the mesh parameter. So here we can try some small number, for example 5. Okay, do not use very small value. Okay, and I can reduce it further, like 2.5. But this one is good enough. Okay. For this mesh, the quality is good. All the meshes have a similar size. However, if you see some corner has very tiny meshes, it means that your geometry is not precise. You need to go back to your draw mode to change that, then inspect your mesh again. Right after the draw mode, I would recommend you do this check, because the PD coefficient and the boundary condition will take a longer time to set, because you have this lots of regions. It will take a longer time to complete. And if you completed all the PD coefficient setting, then you found out that your geometry is wrong, you have to redo everything again. That will waste lots of time, because every time you change anything in this draw mode, you have to re-enter all the information for your PD mode and also the boundary condition mode. Therefore, we need to make sure that your geometry is right before you enter your PD coefficient. Okay, now we save it. We go to the boundary condition mode. Here, we are going to apply the mirror or reflective boundary condition along the diagonal line and also the bottom line, because these two boundaries, they are symmetric axes. We need to apply the mirror boundary condition, and this external boundaries will be applied by the vacuum boundary condition. Okay, and we press Ctrl A to select everything. Okay, everything is highlighted as black. Double click. We use the Neumann boundary condition. We set everything to mirror, so everything here is 0. Then we set the external boundaries to vacuum. So hold your Shift key and select all those edges. Double click. You only need to enter this one as 0.646922. Okay. 0.46922. Okay. This will set the external edges to vacuum. Okay. Press OK. Next, we go to the PD mode. For the PD mode, it will take some time to complete, because there are many regions. Okay, many regions. Save. And recall that there's a small bug. You need to change all the C together in all the subdomains in order to change the C11 to not equal to C22. Okay. Otherwise, it will not allow you to do so. So we press Ctrl A to select everything. Okay, just Ctrl A, select everything, and double click. Okay, double click. Change it to eigen mode. I'm going to set all the subdomain to material number 2, so that everything is material number 2 first at the beginning. So this one will follow those formula. This is your C11 is your D1. C22 is your D2 for material number 2. Okay. This is A11 is sigma A1 plus sigma S. Okay. Sigma A21 is negative sigma S. Okay. Here sigma A2. D11 is sigma F1. Okay, and this one is 0. We need to double check to make sure that everything is entered correctly. Okay, press OK. Next, we are going to enter the material number 3. We need to hold your Shift key and select out the material number 3. Material number 3 subdomain. So 5 here, 3 assembly here, 1 assembly at the bottom. Okay. Double click. We set it to material number 3. Okay. Then double check the value. Okay, press OK. Material number 4 is here. Set to material number 4 cross section. Now double check the value entered. Okay, press OK. Last one is the material number 5. Okay. Double click. Enter material number 5 value. Okay, press OK. Also save it. And change the solve parameter to 0 to 1. Okay. Press OK. Then we can solve it. Okay. And I'm going to change this this one to jet. Okay, and that will look much better. Okay, so U here is my group 1 neutron flux. Okay, group 1 neutron flux, and looks good. And V is my group 2 neutron flux. Okay. And everything here is positive, so I don't have to manually change that. However, if your value is all negative, you just need to choose user entry and put a negative U or negative V. Okay, here. You can also have the height. Okay, plot. So this is the 3D view of the first group neutron flux. Okay, U is the first group. And if you change everything to V, to a plot, this will be your second group neutron flux. Okay, we see that at the center of the core, this value will be higher, and also in the water region, and this value is higher. Okay, that will meet our neutron physics. Okay, and this will conclude the PDE modeler. Okay, next we are going to write a piece of script to calculate the assembly power, the normalized assembly power. So I close this one. If you want to save those figures, you can just you can do so. Okay, just file and save as. Okay. For this one, you will have to do the screenshot. Next, you export the solution. Okay, export a solution, export U and L, export the mesh, PET. Okay, export the mesh. I should put it here. Okay, PET. Okay. Then we will close this one or save it. Minimize that. Okay. And this is the calculation. Okay. On your right hand side in this workspace, you should have those 5 variables. I'm going to get a new script, save it, save this one to post processing or power calculation, whatever you want to call it. First, I'm going to display the eigenvalue. No, not eigenvalue, the multiplication factor. So k is equal to number to string, and the L contains the eigenvalues. Okay, you see that inside this L, it has multiple values. We only need the first one because we want the lowest eigenvalue, and the reciprocal will give us the largest multiplication factor. So 1 over L1. Okay, 1 over L1. We run it. Okay, so this is our K. Next will be the difficult part, which is the power calculation. For the power calculation, what we need is this function. Okay, we need to do some preparation for this function. The first one is the assembly map. Okay, assembly map. So 3 dot, get the new line. We use 0 to pad the empty assembly. So we have a 6 here, then 5, 5, 0. Okay. To make sure that it matches the assembly map. Then double check this array. Okay. The 3 dots means that we are going to get a new line. Okay, and this line will be connected to the previous line. Each semicolon will separate 1 row. So we have 7 rows and 9 columns. Okay. Next one, we need to define the size of each column. Okay, I call it the length of x. It will be 1 row, 7 columns, 9 columns, times the assembly pitch. Okay. So if you run it, simply this one will give you 9 identical values, okay, because they have the same size. Then Ly is the same. Ly is equal to L, the first 7 element of the Lx. Okay. Next, we need to have our cross section. So for this cross section is mu sigma f. So first row is for material number 1, but material number 1 is not used there. However, we still need to have the first row for the material number 1 because the function will looking for the second row for material number 2. Okay. So we enter 2, 0 here. This one is for group number 1. This one is for group number 2. Okay. And enter any number there because they are not used. Next, we enter the fission cross section for material number 2. Okay, then double check the value. Okay, everything looks good. Next, we save it. Okay, click here, save it. And next, I'm going to use this function. Okay, and just double click this one, and I'm going to copy this part. Okay. Do not alter anything inside this function unless you understand what you are doing. Okay. So we put a semicolon there. So here we have PTU, that is from this result. Okay, rectangular array is this map. Okay, this map. This lower left coordinate is the lower left xy coordinate of your core, okay, of your geometry. So we place the lower left corner at the origin, so that is 0 and 0. It must be inside this bracket because it should be a vector. So x is 0, y is 0, so at the origin. Then length x, length y, we just define here. Cross section is VF. Okay, it's VF. The next one will be the total power. Okay. For this total power, it is the total field assemblies inside your model. Okay, inside your model. We can calculate this total power in this way. Okay. So in the first row, we have a 7.5 field assembly. Okay, 7.5 field assembly. And we only need to count the field assembly. So material number 5 is water. It is not a fuel. It is not fuel. And we do not count the material number 5. So in this total power, we need to count the material number 2, 3, and 4 only. And the half assembly is counted as 1/2. So the first row from the bottom, we have 7.5 assemblies. 7.5 field assemblies. Then the second row from the bottom, we have 6.5 field assembly. Then we have 5.5. Okay. Then 4.5. Then 2.5. Then 1.5. Next, we can write. You will see that total power is 28. It means that there are a total of 28 fuel assemblies inside your 1/8 model. Okay, inside your 1/8 core, and the total number of assembly inside the real entire core will be 28 times 8. Okay, 28 times 8. The thermal power result is stored inside this power array, so we can just open this one and look at this value. I need to mention that this diagonal line, the power along this diagonal line is just the 1/2 of the real power, because we only modeled the half of the assembly inside our model. So when we perform the numerical integration, we only get 1/2 of the power. However, in the real reactor, those assemblies going to produce twice the amount of this value. Therefore, we need to manually double those values. Okay. There are a couple of ways to do this power correction. Here, I'm going to use a loop. Okay. So I'm going to get a row. It's from 1 to 7. So we have 7 rows. Okay, 7 rows. And this is our diagonal line. Okay, this is our diagonal line from here until here. So this is the diagonal line. So in the first row, in MATLAB, this is the first row. Line 4 is the first row. So when the I row is equal to 1, the column need to be corrected is the number 7 column. Okay, number 7 column. So that is 7 rows plus 1 minus I row. Okay. So you see when this I is equal to 1, this one is equal to 7. Okay. So that is 1, 7. Then when I is equal to 2, this one is equal to 6. So it will select this element. Then when the I is equal to 3, this one will be equal to 5. So this one is number 5 column. So it will select this one for correction. Then times 2. Okay. Then we just disp this power array. Save it, run. Okay, so this is the result. Okay, I move this one wider so that everything can be displayed in one row. Power array. Okay, this is our result. And until here, it concludes the normalize the power calculation, and I will use the slides to review what we have accomplished. Now we have demonstrated how to solve this multi-assembly rectangular reactor, and I'm going to use the slide to review what we have accomplished. First, you need to choose the generic system so that it can solve the two differential equations coupled together. Then it will be the draw mode, and you need to draw the first assembly. And before that, you need to decide where you want to place your origin. Normally, we place the origin at the center of the reactor. Okay, at the center of the reactor. That will make your life much easier. Certainly, if you want, you can place this origin at any other location you want. For this problem, all the assembly, they have the same size, and it is a square with the side length of 21.608 centimeter. So the first step is to draw a square. Okay, draw a square, and you have the width and the height both set to be 21.608 centimeter. And we will place this assembly, the first assembly, the lower left corner at its origin. So this is the assembly at the center, okay, close to the center. Then you need to adjust the size of your canvas. Okay. You need to calculate what will be the total size of your reactor. Okay, what would be your total size of reactor? In this problem, we are modeling the 1/8 of the core. So we have 9 assembly along the x direction and 7 assembly along the y direction. So apparently the x direction is larger. So if we have 9 assemblies, then along the x direction, then the total length along the x direction would be 21.608 times 9. So that is 194.472 centimeter. Okay. And we will choose the 200. So we adjust the axis limit to show it from 0 to 200. Or you can also make it to show from maybe negative 10 to 200, so that after you complete the entire geometry, you can view the entire core on your canvas. Next, we will duplicate this shape R1 in order to complete the first row. Okay. The first row contains 7 assemblies. We have already drawn the first assembly, so we have 8 assembly left. Here we are going to take the advantage of the copy and paste function. So what you need to do is that you need to select the R1. Okay, select the R1. You have just the one assembly. Select the R1, and then press Ctrl C. Okay, on Windows that's Ctrl C. On Mac that's Command C. Then you can press Ctrl V or Command V. Okay, then it will pop up a menu. Okay, as shown in the figure in the upper right corner. Okay, this is paste the figure. Okay, you are going to duplicate this assembly along the x direction. Okay, along the x direction. So there will be no y-axis displacement. So we are going to enter the 0 in the y-axis displacement. Okay, so all those duplicated assembly will stay along the same row. Then the pitch of those assemblies are 21.608. Okay, so they are tightly packed together. So each assembly will be moved to the right for 21.608. So we enter the assembly side length as the x-axis displacement. Okay. You are going to create 8 additional assemblies. Therefore, you need to enter the 8 as the number of repeats. Okay, 8 number of repeats. You need to review this dialog to make sure that everything is correct. Okay. When you click OK, then those 8 assemblies will be generated for you. There's no undo, so if you make some mistake, you will have to delete those created assembly and do it again. After this copy and paste, you now have 9 assembly along the first row. Next, we are going to create the first assembly in each row. So we have 7 rows. We have already finished the first row. We have 6 rows left. Okay. So we are going to create the assembly along the diagonal line. Again, we are going to select the R1 only, the very first assembly only. Okay. Do not select more than one assembly. Select R1, then press Ctrl+C, then Ctrl+V. Okay, Ctrl+C, Ctrl+V. You get another paste dialog. In this dialog, you can see that for the diagonal line, each assembly is going to move to your right for one pitch, that is 21.608 centimeter. It will also move to the y positive direction for another pitch, so that is also 21.608 centimeter. So in this case, we are going to enter this 21.608 centimeter as both the x-axis and y-axis displacements. Therefore, it will move to the right at the same time. It will also move to the up. Okay. So we have 7 rows. We already have the first row. Then we need to create another 6 rows. Okay. So we enter the 6 as the number of repeats, and the result is shown in the figure located at the lower left corner. Okay. The lower left figure shows the after you paste this diagonal assembly. Then we repeat this process to create each row separately. For example, you select SQ9, then you generate all the assembly for this row. Then you select SQ10, you generate assembly for the third row until all the assembly are generated. Then the final shape of this multiple rectangular assemblies is shown inside this figure, inside this red block. Next, we need to draw a triangle in order to cut this reactor, so that it will be exactly the 1/8 of the core. So we use the polygon tool. Okay, use the polygon tool, and you draw this triangle roughly. Then you need to double click this polygon P1 to adjust the coordinate of each points. Okay, of each points. And apparently the bottom point is located at 0, 0. Okay, 0, 0. Then the upper right corner of this P1, you can select any location you want, as long as this triangle will cover this unwanted region. Okay. Here I use 160 and 160. You can also use 170, 170. Okay. As long as it is big enough. Then the third point will be 0 and something. Okay. 0, 160 will work, or 0, 170 will also work. Okay. And another thing you need to remember is that after you enter each x or y value, when you change this polygon coordinate, you must press the tab Otherwise, what you have entered will not be saved. Okay, if you just click the OK, it will not be saved. You need to press the tab, then press the OK. Then you need to adjust this set formula. Recall that the negative has higher calculation priority than the plus in MATLAB PDE Toolbox. Therefore, when do the union of all the rectangular first, then we do a bracket of all the to enclose all the rectangular square, then minus P1. Okay. So before entering the boundary condition and the PDE coefficient, I would highly recommend you generate your meshes first in order to identify if your geometry is correct or not, because at this moment the geometry is complicated and the student tend to make mistake. And if you spend lots of time and enter the boundary condition and PDE coefficient, then later you discover that your geometry is wrong, then you have to go back to your draw mode and redo everything again. That will waste lots of time. Therefore, we'd like to capture those errors before you enter your boundary condition and PDE coefficient. The small imperfection of your geometric model can be revealed by this mesh quality. Okay, so you just go to your mesh mode and you use the menu mesh parameter. Then you enter the some edge size and generate this mesh. You should see the uniform mesh as shown in the upper right figure, which is a good quality of the meshes. However, if your geometry is not precise and from this geometric calculation, from this Boolean operation, you get the geometry that has small imperfection at a certain boundary, as shown in this lower right figure. The mesh will be produced. The very tiny mesh will be produced around those small corners. So as shown by this lower left figure, if you see those very small, very tiny meshes around some corner, around some location, those places will be the wrong geometry. If you zoom in, you will see the imperfection of that geometry. So this example is caused by the wrong coordinate for the triangle P1. It's not the wrong coordinate, this is just the coordinate that is not very precise. For example, you enter 160, 160, you should enter 160, 160, but you entered 159 and 160, then that will give this diagonal line not very precise. That will cause this kind of error. So if you see this kind of tiny meshes, you need to go back to your draw mode and fix your model before you go to the boundary condition and the PDE coefficient, because the boundary condition and PDE coefficient will take longer time to set. Remember, if you change anything in your draw mode, you need to reset, re-enter all the values in your boundary condition and PDE coefficient, because those numbers will not be preserved. So next is the boundary condition. So we go to the boundary condition mode. In this geometry, the bottom edge and the diagonal line will be set to the mirror or reflective boundary condition, because they are internal boundary and they are the symmetric axis. And all other external boundaries will be set to the vacuum boundary condition. So there are many edges So we just for simplicity we just click the Control A. Okay, press Control A to select all the edges. Then we set everything to mirror and reflective, to mirror or reflective, as shown by the first figure. So everything will be 0. Then we need to select all the external edges. Okay, we need to select all the external edges. So those edges should be set to the vacuum boundary condition. And then the vacuum boundary condition, the value you need to enter is shown in the lower right figure. Okay, just Q11 and Q22 are 0.46922, and all others will be 0. Next step is the PDE coefficient setting. We need to switch to the PDE mode. And remember that we need to set all the subdomains together, because we want to set the C11 not equal to C22 for all the subdomains. Otherwise, there will be a bug. It will not allow you to do so. So we just simply click Control A, select all the subdomains. Okay, and then we just set everything to field 2. Okay, set everything to field 2 according to this formula. Okay, according to this formula. So C11 and C22 they are D1 and D2. Then A11 is sigma A1 plus sigma S. A21 is negative sigma S. A22 is sigma A2. Then A12 is 0. For the D, remember that you need to set the D21 and D22 to be both 0. Okay. Then D11, D12, they are mu sigma F1 and mu sigma F2. Follow this material 2 cross-section and enter those data into this PDE coefficient setting. And also make sure that you choose the eigen mode. Next, you need to deselect everything and select only the field 3 region. Okay, select all the assembly that is filled by the field 3. Okay, the third material. Then follow this, follow the same equations and enter this material 3 cross-section. Then do the same thing for material type 5 and material type 4. Okay. And then change the sort parameter. Reduce your eigenvalue search range to 0 and 2. Then you can obtain the neutron flux figure. So the top 2 figures, the upper 2 figures are the top view, then the lower 2 figures, they are 3D view. So this will conclude the PDE modeler part. Next, we will calculate the assembly power. First, we display these eigenvalues. So we display k is equal to number to string inside this bracket, that is 1 over L1. Okay, so 1 over L1. Okay. The variable L stores the eigenvalue. Then we only use the very first eigenvalue, the smallest one. Then you get the largest k. Next, we will calculate the normalized assembly power. First, we need to define a matrix that will store this material map. Okay, material map. So we have 9 by 7 matrix. So along the x direction, so we have 9 columns. Then along the y direction, we have 7 rows. Okay. Then we just enter those numbers according to the material map. Okay. So this 2, for example, here at the lower left corner, this 2 means material number 2. Okay, material number 2. And we use the 0 to pad those empty assembly. Okay, so that it will be a square assembly. Next, we need to define the length of each column and also the length of each row. Okay, so the size of each assembly. So the length along the x direction will be 21.608. Then repeat 9 times. So this ones that will give you a row vector. Okay, so it is 1 row, 9 columns, and everything will be 21.608. Then Ly will be similar, but it will contain only 7 entries. Next, we need to define another matrix to store the fission cross section. Okay, store the fission cross section. And here, the largest material index is 5, so we should have 5 rows. Okay, 5 rows. Although the first material is not used in this problem, but you have to put a row there. Okay, because the program will try to find the 5th row for the number 5 material. You just enter 0 and 0 or anything you want, because this first row will not be used. Then you get the mu sigma f for material number 2. So you have group 1 and followed by the group 2. So material 2, material 3, material 4, and material 5. Material 5 has is a non-field material, so it has 0 and 0. Next, you need the MATLAB script called PDE Tool_power_rectangle. And you need to download this file from the Blackboard and also place this file in the same folder of your script. Okay, because now we are going to use this script to calculate your normalized assembly power. Okay, inside this one, it will perform the numerical integration and integrate this reactor power inside each assembly. Okay, inside each assembly. The first one you need is the PTU. Okay, you need to export your solution and export your mesh. Okay, the PTU. So this is mesh and your solution. Just put it here. Then the next variable is your material map. So this is your rectangular array. So this variable is rectangular array. So you put this variable here. Okay. Next one is the lower left coordinate of your geometry. And previously, we set the origin at the reactor center. Therefore, we just put 0, 0. Then if your lower left corner has different coordinate, then you enter that value there. Then you do the dimension of each lattice. So this is the size of each assembly along the x and along the y direction. We previously defined in line 13 and line 14. Okay. Next one is the fission cross section. We defined in line 16. Okay. Next one here is the number of field lattice inside this core. Okay, number of field lattice inside this core. This is called normalization factor. Okay, you need to tell this function how many field assemblies are there inside your entire geometry. So you just need to count the number of field assembly. You only need to count the field assembly. If this assembly is not field, you do not count this assembly. For example, in this model, we have the water as the material number 5. Therefore, anything labeled by material number 5 will not be counted. And another thing is that if you are unsure about this is fuel or not, you just need to check this mu sigma f. If both mu sigma f1 and mu sigma f2 are 0, then most likely this is non-fuel material. And if you have a positive value for this mu sigma f, then this is a fuel material for sure. So for example, inside the row 1, you have a 7.5 fuel assembly. Okay, so half assembly is counted as 1/2. Okay, row 1 you have a 7.5 fuel assembly. Then the row 2 from the bottom, you have a 6.5 fuel assembly. Then you count that, and the summation will be 28. Okay, you can verify this by yourself. It's very important you know how to count this one. So just the two things you need to remember. One is that the half assembly is counted as 1/2. Later you will see maybe 1/4 of the assembly. And if in that case, then the 1/4 assembly is counted as 1/4. Then if you have a 1/8, then that is 1/8. You just add 1/8. And you do not count the non-fuel material. You count the fuel material only. Enter this 28. Then the result will be stored inside this assembly power. So look at the line 27, then the result will be stored inside the assembly power. Another thing is that along this diagonal line, we only calculated or we only modeled the half, 1/2 of the assembly. Therefore, when we perform the numerical integration, what we get is the half power, okay, half power. But in reality, those assemblies are full assembly. Therefore, we need to restore those assembly power to full assembly power. We just need to multiply this multiply the power along this diagonal line by 2. Okay, by 2. And the algorithm is shown here. So we have 7 rows. So I used the for loop. If you want, you can also manually perform this multiplication. Okay. So then you see that the II will loop from 1 to 7. Okay. Remember, you use the II instead of I, because the I sometimes it is reserved for the complex number. Okay, use I to remove those misunderstanding between you and the MATLAB. For example, here, if the I is equal to 1, then you have assembly power 1 and 7. Okay, 1 and 7 will be equal to the same value times 2. Okay, so row 1 and column 7. So this is the first assembly on the top. Then will be 2, 6. Okay, then the follow-up assembly along the diagonal line. Okay, in the second row. Recall that in the matrix, the first row is here. Okay, is line 5. Then second row is line 6. Okay. Then we display this assembly power to give. Then the final result will look like this. So you will have the K from the display command. Then it is a matrix of normalized reactor power. So the average assembly power will be 1 after this normalization. So everybody will get the same result. Recall that we will not be able to know the actual power unless we know the total power or we know the assembly power of one assembly. Without those information, what we can get is the normalized assembly power. Okay, and from this calculation, you will be able to know which assembly is producing more power and which assembly is producing less power, and by how much. Here I present the menu of this power calculation script. Okay, so this one will take the PTU as the one of the input. Okay. So that is from your PDE modeler. You need to export your result and also export your meshes. Okay. Rectangular array, so that is nx by ny matrix. Okay. So this is your material map. Then lower left corner coordinate will be 1 by 2 row vector. Okay, row vector. So that is the coordinate of your lower left corner of your rectangular ring. Okay. Normally 0 and 0 if you place your core center at the origin. Then the length of x, so it should be 1 by nx, is also a row vector storing the y's of each lattice. And this nx should be equal to the nx for the rectangular array. Okay, these two should match. Okay, otherwise it may crash the calculation. Then ry is the size is 1 by ny row vector storing the height of each lattice. Okay. Then the xs is the cross section. Okay, it's the cross section of all the materials, and the size will be n material by 2. Okay. We only calculate the 2 energy groups. Then there is the total power. So this is used for assembly power normalization, so that the summation of all your assembly power will be equal to this value. And you simply just need to count the number of field assemblies inside your model. Half assembly is counted as 1/2, then 1/4 of the assembly is counted 1/4, then 1/8 is counted for 1/8. Yeah. Then the result will be stored inside this power array. Okay, so power array is equal to this PDE2 power rectangular. So the result is stored here, and you get the nx by ny matrix storing the calculated normalized assembly power. Another thing is that this script is not a MATLAB built-in function. Therefore, you have to place this script together with your post-processing script, okay, in the same folder. This slide explains the basic algorithm used by this power integration function. So this function automatically divides each rectangular grid or field lattice into 8 equal triangles, as shown in this figure. Each triangle subdomain includes multiple meshes. Okay, there will be multiple meshes inside each of the triangles. Mesh crossing a subdomain boundary is also allowed because it will perform the numerical integration. The function interpolates the neutron flux solution of all energy groups at 7 Gauss quadrature points and perform the weighted summation to numerically integrate within an arbitrary triangle domain. This algorithm is valid with any type of partial rectangular lattice on the symmetric axis, because the shaded area or this blue area always cover one or more triangle subdomain. Okay, always exactly cover one or more triangle domain, no matter how you cut the assembly. For example, for rectangular core diagonal line, it may be half like the third figure here, or 1/8 assembly, or the first figure. And it will exactly cover one or more triangles, so that this algorithm will always work. Then, once the integrated neutron flux is obtained, the reaction rate is calculated by this function. Okay, this function shown here, or this formula. Recall that the reaction rate is the macroscopic cross-section multiplies the neutron flux. Here, we will also do the summation of all the reaction rates of each group. Here, this phi g is the area integrated neutron flux of group G calculated by the aforementioned 2D numerical integration. Finally, the last step, the thermal power or the fission reaction rate is normalized so that the average assembly power is 1.0, or the total reactor power is equal to the number of the few assemblies in your model.